All right, welcome to section 4.3 where we are continuing in chapter 3 on our exponential and logarithmic functions. We are going to look at the inverse of an exponential function with this logarithmic function. So it is something probably new to you. In the last section we looked at some exponential functions that were more real world based, but the logarithms are the ones that will undo that exponential function. So it is something that is one-to-one. It will have an inverse, and so basically just like a square root undoes a square and dividing undoes multiplication, we have logarithms that undo exponentials. So let's first give a definition of that. And so for the value of x greater than 0 and any b greater than 0, where b is not equal to 1, then we get this. We get y is equal to log base b of x is equivalent to b to the y equals x. So this is going to give us the definition of how these things are related. And I always tell them kind of to students to do this in a circle so that you see that. So in this sense, if I talk about doing it in a circle, we would, in order to change to an exponential value or an exponential equation, we would take b to this power is equal to this value. A lot of times I'll go counterclockwise, but the way this is set up, we would go there. Also, to change from an exponential to a logarithmic, we would say log base b of x equals this y. So the idea of a logarithm is that you're actually finding the power that makes that true. So in this function, log base b of x, it is read just that. Log base b of x. Okay? This function value is going to equal the power that makes that exponential equation true. So that is what we have here in this answer. The answer to a logarithmic problem is the power you take the base to in order to get the number in the end, okay? So let's first practice taking logarithmic functions or forms into an exponential form. And again, do a circle to help you out. Because in order to solve these things, a lot of times we do go into the exponential form and take it out of that logarithmic form. So let's do that. Kind of doing into the exponent form. So I'm going to end of this form, b to the y equals x. So we take our base, which is 7, to this power has to equal x. So 7 to the third equals x. That's changing it to exponential form. Do it again. Base b to the 2 power is equal to 25. So b squared equals 25. Now, the next piece, we have 4 to the y equals 26. And that is just an exercise of getting from the logarithmic function down to exponential functions. Now, the next piece here is changing it in the other direction. Can we now do this version given this exponential form? We're going to start with our base. Log base 2 of x equals the power. So log base 2, that's a little subscript, of x equals the power of 5. Again, go in a circle. Log base 2 of x equals 5. Let's do log base b of 27 equals 3. So log base b, which is a subscript, of 27, b of 27, equals that power, which is 3. For the final one here, we would do log base 5 of 33 equals y, of 33 equals y. And that would be changing it to a logarithmic form as opposed to keeping it in exponential form. Now, this again, I said, is helpful if you're trying to solve some of these equations. It's much easier sometimes to change things into that exponential form than it is to keep it in the log form. So we're going to do just that and see if we can solve these. So if I take 2 to the 4th power equals x, 2 to the 4th power equals x, therefore, to solve for x, I just need to figure out what 2 to the 4th is. Well, 2 times 2 times 2 times 2 gives me 16, and that is a valid answer. Again, take the base to the power equals this value. So 1/2 to the 5th power is equal to x. Well, if I'm solving for x, which is what we do when we solve an equation, I'm going to now simplify this by taking 1/2 to the 5th, or there's a property with exponents that says I can take 1 to the 5th and 2 to the 5th. I can split that up. So 1 times itself 5 times is 1. 2 times 2 times 2 times 2 times 2 is 32. So x here is going to equal 32. On our last type of problem here with this, changing into exponential function, we get 3 to the 2nd power equals this expression of 2x plus 3. And now it's not as easy as these, where I just have to simplify the number side. I actually have to solve this for x. So I'm going to first make this a 9 equals 2x plus 3. Then we're going to subtract 3 from both sides. And I get 6 is equal to 2x. And when I divide by 2 each side, x here is equal to 3. And that would be our final answer. Now, double checking. Remember, this term right here had to be positive each time. So if I throw in each of those numbers, then it does become positive. So we're good to go for that. All right, let's try some of these down here. Use this idea to actually find some logarithms. So now we don't have an equation, but a lot of times to solve a logarithm, I'm so encouraged to make an equation because x is what we're looking for. What is that equal to? Let's make it an equation and change it into our exponential form, going counterclockwise, and then we can solve. So if I say 10 to the x equals 100, well, there's my exponential form, and now I can look at that and say, okay, can I actually change things to the same base? So for example, here I have a base of 10. The question would be, can I take this larger number down to a base of 10? Well, is it 10 to some power equal 100? Absolutely. It is 10 to the 2nd power gives me 100. So that equals to this left side. And once you have bases that are the same, you can now extract your powers and say, okay, well, if these bases are the same, then for that to be equal, those powers have to be the same. So x has to equal 2. And that would be the answer to this piece right here. Now, does that make sense? 10 to the 2nd power equals 100? Absolutely. Now, if you could do this without, I say log base 2 of 8. Well, 2 to what power is 8? If you want to kind of evolve yourself to do that, 2 to what power is 8? Well, that's a 3rd power. So if you do this exact same process, you're going to get the same answer here, but sometimes you can eliminate a lot of this work just by asking yourself that question. 5 to what power is 1 over 125? This one is a little bit more difficult. So let's do this into exponential form. So I get 5 to what power is 1 over 125. Now, again, the idea is to get the same base. Well, can I write 125 as a base of 5? Because that's the one I'm working with here. And the answer is yes. I can write that as 1 over 5 cubed. But because I have that in the denominator, notice we have this 1 over that. Well, we don't want that 1 over that. I want 5 to some power so that I can equate it to that 5 to the x, and then I can put my exponents together. Well, there is a property of exponents, if you recall, that it allows us to bring this base up to the top, and that property is the property of negative exponents. So if I make that a 5 to the minus 3, normally we're taking that and doing 1 over 5 cubed, which gives us 125. But in a sense that we're working backwards, now I have my bases that are the same. I can extract out those powers. Therefore, x equals negative 3. That is what this logarithm is equal to. All right, let's try another one. Let's set that equal to x. 36 to the x power has to equal 6. Well, now this time, the lower number's over here without the exponent, but the question would be, can I write 36 as a base of 6? And the answer is yes. That is 6 squared that I have to take to the x power equals this 6 to the 1st power, if we want to write that in there. And so now I need to remember that a law of exponents says that if I have a base to 2 powers, that is when I multiply those powers together. So I could write this the best as 6 to the 2x is equal to 6 to the first. Now we have bases that are the same. We now put our exponents together. Now, unlike before, we had x equal and x equal. Now we don't have x equal, but we can solve by dividing by 2 to get x equaling 1/2. And that would be my answer for that one. Now, an x to the 1/2 power. 36 to the 1/2 power, if you recall with fractional exponents, is the same as the square root of 36 to the first, which is the square root of 36, which is 6. So that jives out and that works out to give me the answer. All right, so this might include a fractional exponent. If you remember, that exponent inside there is a 1. Let's go ahead and set that equal to x and write our exponential form as 3 to the x equals the 7th root of 3 to the first. Now again, this is where you have fractional exponents. If I have the mth root of x to the n, that's the same as x to the n over m, where I do power over root, power over root. So here, this would be 3 to the power over root gives me 1 over 7, which then has the same basis. Therefore, my exponents have to equal. So our exponent here is 1/7. That looks like a 2. That should be a 1/7 for our answer there. Okay? All right. Maybe I can get that piece off of there. We're going to turn to the next page. Okay? So we've found how to do logarithms. Now we're actually going to look at a special base that we call the natural exponential. So we are going to kind of equate this to the number pi. Actually not equate it in any way other than saying that it is an irrational number. It's one that is a special number, a constant that's set in stone, but it does not repeat nor does it terminate. So the natural exponential is an irrational constant symbolized by the letter E with an approximate value of 2.71281828. Okay? Now, if we keep going on and on and on, it almost looks like it does repeat, but it actually will not if we continue out. Now, the graph of f of x equaling e to the x looks like this, where if I were to do some t-table, okay, where I let x be 0, let x be 1, let x be 2 if we want to do that, we can plug 0 into here and e to the 0 power. Well, here's another thing you got to remember, that anything to the 0 power is 1. Make sure you remember that, because on any exponential, anytime that I put 0 in here, no matter what base that I have, 2, 3, e, pi, this value is going to be 1. If I plug 1 in there, then I get e to the first, which is that 2.718 in approximation. So if I were to graph 0, 1, that's going to be this dot that's right here on our y-axis. Then over 1 and up 2.718 gives me somewhere about here. Now the exponential, if you were to plug in all other values, say -1, -2, 2, 3, whatever, to get lots more on there, you will get a graph that looks like that. Now, another graph just over here on the side for extra info, that 2 to the x, it's going to look very similar, but in its t-chart, when you put 0 in, you get 1. When you put 1 in, 2 to the first is 2. Then you still get the same look. It's just that your numbers are off just slightly. Okay? And that's okay. So when we undo this natural exponential, we're actually going to have a natural logarithm, because if I'm going to go backwards of that. Hence, this is our next little piece here, because there's two that are very special. One that has a base 10 and the other that has that natural exponential as a base. So let's first talk about the common log. And this is something that you will actually see on your calculator, because anytime you see log on a button on your calculator, it is understood to be of base 10. So we write it as log of x. Notice we don't put a base down there. It is assumed to be a 10. Just like if I have an x here, there's an invisible 1 in front of here. So for the natural log, this is where we have a base e, and it's written as the natural log of x. So here's where I'm going to stop and make sure that you realize that those are lowercase l's. Anytime that you're putting into like MyOpenMath or an online operating system, you want to write it like that or like this, but you want to use l's and not capital I's. I've seen that in the past, okay? All right, so let's practice these exponential equations and taking them into a logarithmic equation. The idea is still the same. I'm still doing log base 10 of 100,000 equals that power, but this time, instead of writing that base 10, I'm not going to write a base. Instead of writing that base of e, I'm not going to write a base. I'm going to write ln. So log base 10, we can just write as log, of this 100,000 has to equal 5. That is what we want to write. If I do this log base b of x equals 7, then that is the natural log. So the log base e of x equaling 7, that would be if I don't write the shortcut, but you don't want to leave it like this. You want to write it as the natural log of x equals 7. So using the natural log when you have a base e, using the log when you have a base of 10. So 10 of this is equal to that. So let's do log of the 1 over 10,000 has to equal -4. And that is the logarithmic equation that would equate to that. Okay, now let's go backwards. Going backwards gives me going into the exponential form. And if you need to write in a little base there, that's supposed to be a little e. Log base e of 10 equals e to the y. Then you can do that. So this is the natural or the exponential form for that logarithm. Here I have log base 10 of 100 equals 2. So to write the exponential form, we're going to go base 10 to the second power equals 100. So 10 to the second equals 100. That's the exponential form. Same way here, I have a base of e, so e to the x equals e to the -3. And that would be my exponential form for that problem. Okay? All right, so now we incorporate some calculator work. So you're going to want to make sure that you know kind of how your calculator works on a 2-line calculator. So again, you're looking for the button that says log, and you're looking for the button that says ln. So if you're on a 2-line calculator, you should be able to print that or write that out just as is. Now make sure you might want to throw some parentheses there, but you don't have to in all cases. So in your calculator, type in log of 0.04, and you should get -1.3979 if I were to go out 4 decimal places. Now, if I were to round that to 3, 1.398. If I were to round that to 2, that would be -1.40. If I type in log of 1045, then you should get a value of 3.019. Let's go to 3 places on that one. The natural log of 15, again, find this button, type natural log of 15. If you're on your phone, some scientific calculators on that, for the 1-line calculators, you have to do 15 and then hit the natural log. You should get 2.708 as an approximation for that. And for the natural log of 0.02, you should get -3.912 as an approximation. So if you are not getting those on your calculator, you need to contact me so I can help you out with your specific one. It's hard because multiple people have multiple different types of calculators. So it's good to make sure that you know your specific one. All right, so let's talk about some basic logarithmic rules. First one being, what if I have log base b of b? Well, let's see what we can do. If I let that be x, I'm looking for b to what power is equal to b? Well, because if I do it in an exponential form, then this power, invisible, is 1. Bases are the same, therefore my powers have to be the same. That will always equal 1. Because 1 is the exponent in which b must be raised to in order to obtain b. Now, log base b of 1 equals, well, let's think about the exponential form. B to what power equals 1? B to what power equals 1? Well, we kind of talked about that actually up here as one of those things that you needed to make sure that you remembered. Well, what power is that? That anything it is to that power equals 1? It is 0. B to the 0 power equals 1. Therefore, that logarithm is equal to 0 because 0 is the exponent to which b has to be raised to get 1. Now, the next two are kind of ones that identify how that you undo that. If I have log base b of what equals b to the x, so b to the what equals b to the x. Well, bases are the same, therefore my exponents are the same. And this would be the case where kind of our log would cancel out my base, leaving me with just the power. Likewise, if I do b to the log base b of x, that's a b down there. Again, these undo each other, so I can cancel those things out, leaving me with just an x value there. Now, this is for when b is greater than 0 and b is not equal to 1. So again, those conditions hold true, just like what we had in our previous part at the very beginning of this section in the definition. All right, so let's try this. If I have 9 to what power is 9? Well, those two things are the same. I'm looking, right up here at number 1. That should be equal to 1. So 9 to what power equals 9? Well, you can convince yourself that that power is 1. What about this one? 8 to what power is 1? 8 to what power is 1? Well, that's in this situation, which tells me I have any base with 1 here as my expression. That is going to equal 0. Why? Because 8 to the 0 equals 1. Anything to the 0 power equals 1. Here, I have a logarithm with a base of 7. I have that same base. Those are the ones that kind of undo themselves. The log undoes the exponential, leaving me with just that power of 8. Again, doing it in a circle. If I let this be x, then I get 7 to the x equals 7 to the 8. And these two things are the same. Therefore, our exponents are the same. And then this one is evaluating kind of this property right here where I can cancel those things out, leave me with an x. So in this case, that kind of in a sense cancels that, leaves me with a 17 as my final answer. Okay? All right. Very good. Now I want to summarize it in this chart. For if I have any base, for if I have the common base, which if you remember the base here is 10, the base here for our natural logarithm is e. So let's just kind of work through those properties that we just had. Log base b of b equals 1. Log base b of 1 equals 0. Log base b of b to the x, those things cancel, leaves me with x. And b to the log base b of x also equals x. Those two things undo themselves. Now, what does it look like for a logarithm, in the common logarithm with base 10? Then I would have log of 10, base and base have to be the same, has to equal 1. So this is the same as that, but with base 10. This, if I have log, I don't write my 10, log of 1, that equals 0. Here I have log of base 10 of 10 to the x is going to equal x. Again, we don't write the 10. And 10 to the log of x, these two things would cancel themselves out and is equal to x. So I know some of that looks a little bit on the strange side. So, what does it look like with the natural log? So here we have a base of, so the natural log of e equals 1. The natural log of 1 equals 0, because my base is e, but I can write it as the natural log. Then I have the natural log of e to the x is equal to x, and e to the natural log of x, those things can cancel, leaving x as well. So I wanted to kind of collate all of that for any base, for your common log base, and for your base of e, your natural exponential. Okay? So can we use those things up above to figure out what we have down here? So the first one, I'm looking at a base of 10. 10 to what power is 1,000? 10 times 10 times 10 gives me 1,000. So that power is 3. Log base 10 of 10 to the 8th. Well, that is where we have a base and a base with a power. So that same base with a power, log base 10 of our base 10 to the 8th power, or 10 to what power is 10 to the 8th? That is equal to 8. Here, those are going to cancel themselves out. That's working with this little property right here. That cancels with that, leaves me with 45. Natural log of e to the 7th, that gives me natural log of e to a power. Remember, those two things back to back cancel themselves out, leaves me with just that power, or you can think of it as e to what power is e to the 7th? It is 7. Here, this is working with the natural log of e to the 13x, so I wanted to show you here, yes, even though this has a variable up here, you can have a variable in the answer. Doesn't just have to be a number. And here, evaluating this piece right here, e to the natural log, gets me back just that expression of 8x. So those would be our answers. And they are pretty quick. They're pretty quick whenever you're kind of going through them, as long as you understand those basic logs. Okay? All right, so this is our last piece here, where we are going into, I don't know why those dotted lines are there, but we'll go with that. Solving equations for exponentials. And our earlier part of our section, we had the same base. So we said, okay, like 10 to what power equals 100? We could write that as 10 squared and then equate our powers together to get x equals 2. But there are times when that is not the case. What happens when you have an equation like 2 to the x equals 5? Where 5 cannot be written as a base of 2. So it's impossible, if it is impossible to write both numbers as the same base, in this instance, we can use the following steps to solve for this exponential equation. So the first thing that we want to do is to isolate the exponential part or the expression when possible. Then we are going to take the log or the natural log of both sides. And technically it doesn't matter. As long as you take the same thing from side to side, then it doesn't matter if you take the log of both sides or the natural log of both sides. This one we normally just do when we have bases of e. Okay? Any other time we would do the log of both sides. Now, utilize the exponent properties for logarithms to bring our variable out front. Now, what does that property look like? That looks like if I have the log base b of x to the power, then I can bring this power out front and then multiply by log base b of x. So this is an important piece that you want to make sure that you know. You can bring that power out front, and most of the time that will be a variable, and then we can solve. So now we want to use our inverses to solve the equation. So basically, if you're multiplying, you want to undo that by division. If you're adding, you want to undo that by subtracting, etc., etc. So let's look at this first one. I have 2 to the x equals 10. Definitely I can't take 10 and make it a power of 2. So we have to isolate our exponential, which it is. It's all by itself. I then want to take the log of both sides. Again, if you're working with any other number besides that base of e, you're going to take the log of both sides. Okay, so I'm going to write this out so we can kind of work with that. Log of 2 to the x equals log of 10. Now, here's where we want to take that property. Notice where our variable is. It's in the exponent. So I want to take that power out front, and I get x times the log of 2 equals the log of 10. Now, if I cover up that x and I just look at the log of 2, remember, that is just a number. We did that on our calculator. It's a really nasty number because 10 to what power is 2? Well, we don't really know. It's a decimal value, okay? But that is just a number. So if I'm trying to get x by itself, this is x times that number. Just like if I have 5x equals 10, I want to get rid of that 5, so I would divide by the number next to the letter and gives me my answer. Now, unfortunately, it's not as pretty as 5 here. This is the number I want to divide both sides by. I get log of 2 that I'm going to divide into the log of 10. Now remember, that goes away. That becomes 1. X equals, the exact value is this, but we're going to go to our calculator and find the decimal value. Now, some of you on your calculators, if it says log, it'll open up a parenthesis, do 10. Make sure you close this parenthesis, then hit divide, and then do the log of 2. That parenthesis is not as important as this one, but you can close that off as well. Some calculators won't have parentheses prompted for you. The one I'm using does not have a parenthesis there. So if you do log of 10, divide by log of 2, you should get a decimal value of 3.322 if I were to round up on that thousandths place. Okay, so that's how we do that. And we can do it again. Okay, so let's try another one. We want to isolate the exponential. Here's my exponential, but I have a 5 hanging out. So I'm going to first get rid of that 5 by dividing both sides by 5. And I get 0.93x to the x power equals 4. Now at this point, the exponential is by itself. Let's take the log of both sides. So I'm going to take the log and the log. And then we're going to use our property to bring our x out front. And we get x times the log of 0.93 equals the log of 4. And we have to, again, realize to get x by itself, I'm timesing by this nasty decimal. So we're going to divide by log of 0.93 and divide by the log of 0.93. That goes away, and now I turn to my calculator to figure this out. So if I do the log of 4, divide by the log of 0.93, then I get the number negative 19.103 if I were to round that. Okay? All right, let's try another one that's very similar to the last one. Very similar because I have this 5 hanging out, but it's different because I also have this 3. So let's first get rid of that 5 and get rid of that 5. We get 1.07 to the 3x. Now, this you can divide out, and it's not too bad. It's just a 0.4. But you can keep it as 2/5 if you so choose. Now that we have our exponential by itself, and I have a number down here and not an e, I'm going to take the log of both sides. So take the log here and the log there. And because I have that variable in the exponent, I'm going to take all of that out front. So I get 3x times the log of 1.07 equals the log of 0.4. Now, to get x by itself, notice we are multiplying all those together. So that's times, that's times. To undo that and get x by itself, I first have to get rid of the 3, and I have to get rid of that log base 10. Oop, not 10. Log base 10, yes, of 1.07, sorry. And so now that's going to go away, and that's going to go away, but I have to do the same thing over here. And so now those cancel, leaves me x on the left. And again, I'm turning to my calculator to divide that log of 0.4 by, now down here, if I were you, I would put parentheses around that and do divide by parentheses 3 times the log of 1.07. And what you should get is negative 4.514 as the decimal approximation for this. So again, if you're having trouble getting the right decimal to come out of your calculator, please contact me so we can work through that. All right, so the last one. Let's do this one. Now notice here, here's my exponential. It is not by itself, and this time I have a subtraction here. So if I wanted to kind of get this by itself, I first have to get rid of that 50 by adding 50 to both sides. And I'm left with 100 e to the 2r equals 130. But I'm still not isolated with my exponential. So I'm going to undo that by dividing by 100. This goes away, leaves me e to the 2r. And I'm ready now to take my natural log of that. Equals, well, I can cancel that. Again, you can keep it as 13 over 10, but that would be a decimal of 1.3. Now, exponential by itself, number 2 in our box above, says that we now take the log or the natural log of both sides. Because that is a natural exponential, I would encourage you to take the natural log of both sides here. And now you have to bring this out front to get 2r natural log of e equals the natural log of 1.3. But we talked about the natural log of e up here in this very top chart. What was the natural log of e? Right here. That is an invisible power of 1. So that's actually just a 1. So we can get rid of that if you realize that that is 1. So we don't really have to divide by 1. But I can divide by 2 here. And divide by 2 because now that goes away and I'm left with r equaling, going to our calculator, the natural log of 1.3 and dividing that by 2 gives me 0.131 if I were to round it to 3 decimal places. And that would be our final answer there. Okay, so that is our first look at logarithms. In our next section, we're going to do a little bit more working with logarithms by finding out there are 3 laws of logs that we will use, properties for those, and we will be able to use that to solve even more equations with our logarithms. So until next time.